I'm Dr. Kayla Ryan, geophysicist and space weather researcher at 8:30 Universal Time. NASA and NOAA space weather monitoring systems confirmed a powerful X-class 4.0 solar flare erupting from the same active sunspot group responsible for a recent sequence of intense explosions. This marks the fourth major solar flare in just a few days, following the X1.7, X1.2, and X5.1 events, all recorded within a remarkably short span of time. The earlier three flares were strongly Earth-directed, producing significant coronal mass ejections that resulted in geomagnetic storm levels reaching G4 and even G5 at peak intervals. These storms triggered widespread aurora sightings across unusual latitudes, painting the skies of Spain, Mexico, Arizona, and parts of southern Europe with vivid colors rarely seen so far from poles. Today's flare, however, appears to have a smaller Earth-directed component. Based on NOAA's preliminary space weather models, the bulk of the plasma may have been launched away from our planet, though the shock front could still graze Earth's magnetosphere. Early estimates suggest a possible G1 to G2 geomagnetic storm. Minor compared to last week's displays, but still notable for its timing and intensity. Radio blackout levels reached R3 today, specifically affecting large portions of Eurasia, disrupting high-frequency communication and aviation navigational systems. What has captured scientific attention is not only the intensity of these events, but their curious timing. All four major X-class flares this month were released within a 3-hour universal time window, suggesting a rhythmic pattern in the active sunspot region's energetic behavior. It is rare for solar events to repeat with such consistency, especially across separate days and varying levels of activity. But this flare is not just another solar event. It may be part of a larger cosmic pattern unfolding this month. The active sunspot region responsible for all four major X-class flares is now classified as a complex beta-gamma-delta magnetic configuration, indicating significant magnetic mixing and polarity inversion zones within a confined area. This structure allows opposite magnetic fields to overlap, creating ideal conditions for sudden magnetic reconnect ion events. Over the past 2 weeks, satellite imagery from NASA's SDO and NOAA's SWPC revealed rapid structural changes in the sunspot group, suggesting fast magnetic flux emergence from deeper layers of the solar interior. It did not appear as a typical short-lived flare-producing region, but rather as a long-lived magnetic engine capable of both resting and reawakening with increasing intensity. Scientists refer to this behavior as a magnetic resonance window, where certain sunspots enter cycles of rhythmic energetic discharge. Instead of erupting randomly, these regions show repeating time intervals between major flare events, hinting at an internal timing mechanism driven by magnetic stress accumulation. This explains why all recent solar flares occurred within the same 3-hour UT window over multiple days. When the sunspot approaches a solar limb facing Earth, it seems to reawaken, likely because magnetic field lines become better aligned with the Parker spiral, our planet's magnetic connection to the Sun. Shock fronts generated during these eruptions have displayed unusually high proton flux spikes, showing deep collapse of magnetic structures before the flare onset. Even when a coronal mass ejection is only slightly Earth-directed, the shockwave can still strike Earth through magnetic conductivity rather than direct plasma flow. This explains why Earth continues to experience geomagnetic disturbances even when the CME trajectory appears westward. This sunspot is not just reacting to surface pressure. It is behaving like a memory-driven system, retaining energetic patterns, releasing them in time cycles, and reorganizing itself rather than acting randomly. A growing number of astronomers have started to observe an intriguing and unexpected pattern. The most powerful solar flares of this season seem to coincide with the orbital positions and perihelion passages of 3 comets currently moving unusually close to the Sun: 3I Atlas, T1 Atlas, and A6 Lemon. The timing is precise enough to raise scientific interest. On the 21st of October, when 3I Atlas reached its near alignment with the Sun as viewed from Earth, a major X-class flare erupted from the same active sunspot group. Just 2 weeks later, on the 3rd of November, during the near-solar alignment of Mercury and A6 Lemon, another energy spike occurred in the same region of the Sun. Finally, between the 9th and the 11th of November, when Earth and T1 Atlas formed new perfect alignment with the active sunspot group, the Sun released a cluster of 3 X-class solar flares, X1.7, X1.2, and X5.1, in less than 48 hours. These repeated events, aligned with orbital windows of these comets, suggests something more than chance. Scientists are not implying mystical forces, but they are exploring the possibility that passing comets, especially those moving close to the solar atmosphere, may create subtle electric field disturbances. These disturbances could influence a balance of charged particles around the Sun, especially along regions already prone to magnetic stress, such as beta-gamma delta sunspots. Comets carry electrically charged dust, volatile gases, and metallic fragments that interact with the solar wind. When these charged trails cross regions of heightened magnetic complexity, such as active sunspots, they might alter the distribution of plasma, affecting solar wind density and possibly influencing magnetic reconnect ion thresholds. Dr. Kayla Ryan suggests that comets may not cause solar flares directly, but could modulate the energetic environment around the Sun, making flare eruptions more likely when magnetic stress is already high. 3I Atlas has quickly become one of the most studied objects in recent space observations, not because of its size or brightness, but because of its unusual behavior and suspected origin. Astronomers consider it a possible interstellar object, meaning it may not have formed in our solar system at all. Its orbital characteristics, chemical composition, and motion trajectory suggest it could have entered from deep space, possibly even beyond our galaxy. Unlike typical comets, which begin developing their tails as they approach the Sun, 3I Atlas showed almost no visible tail before reaching perihelion. Surprisingly, its tail began forming only after passing perihelion, reversing the normal process. This indicates an unusual internal composition that reacts differently to solar radiation. Satellite data has revealed a metallic-like surface reflectivity, suggesting a possible presence of conductive or ferromagnetic materials, not common in standard comets composed mainly of ice, dust, and silicates. Even more intriguing are the electromagnetic fluctuations detected by NASA instruments, which recorded rhythmic, pulsating emissions that do not align with the typical ionization process seen in comet tails. The fluctuation could imply that 3I Atlas is a highly conductive or magnetically active core. Currently, 3I Atlas sits only 15 degrees off the Earth-facing solar limb, placing it dangerously close to zones where recent solar flares have erupted. Although a comet cannot trigger a solar flare, its position within the Sun's magnetic influence could allow solar storms and charged particle streams to interact with its tail, altering both its appearance and behavior. Some scientists have noted that its tail began rapidly expanding shortly after the last X-class flare. Dr. Kayla Ryan points out that this may not be a simple celestial crossing. In his words, 3I Atlas is not just passing through our solar system, it is interacting with it. On November the 19th and 20th, the solar system will experience a rare geometric alignment involving the Sun, Mercury, Earth, the Moon, and Uranus, forming an almost straight line within a narrow 2-degree angular margin. Mercury will be at inferior conjunction, positioned directly between Earth and the Sun, while the Moon will be at its micro-new moon phase, its farthest position in orbit, appearing smaller and exerting subtly different tidal forces. At the same time, Uranus will be at opposition, making it appear at its brightest in the sky, directly opposite the Sun from Earth's perspective, much like a full moon but on a planetary scale. These alignments create a rare configuration where multiple bodies are positioned to transfer solar wind, magnetic stress, and tidal forces along nearly the same directional axis. This alignment is also connected to a larger heliocentric pattern, the Saturn-Neptune synodic cycle, a 37-year orbital resonance. Saturn and Neptune are currently near conjunction, which some geophysicists believe enhances long-range magnetic stability and influences how solar energy disperses through the heliosphere. While planetary gravity by itself is weak and not enough to cause physical solar events, scientists point out that the combination of gravitational tides, solar wind flow alignment, heliospheric current sheet positioning, and lunar tidal resonance can together modulate solar activity thresholds. In simpler terms, this alignment does not cause solar flares or earthquakes, but it may help synchronize the timing of when magnetic systems are most likely to release stored energy. Geophysicists refer to this as synchronous energy timing rather than direct causation. The alignment can amplify energy transfer between solar wind flow and Earth's magnetosphere, while also influencing internal tectonic stresses due to minor fluctuations in Earth tides. As Dr. Kayla Ryan describes it, it's not gravity, it's energy timing, magnetic symmetry, and cosmic rhythm. In the same window that three major X-class solar flares occurred between November the 9th and 11th, Japan experienced a rapid series of seismic events concentrated near its northeastern coastline. Over 24 earthquakes exceeding magnitude 5.0 were recorded during that 72-hour period, including two notable events measured at 6.8 and 6.4. These earthquakes occurred in clusters along a known megathrust fault zone, where the Pacific Plate subduct beneath the North American Plate. What makes this activity more concerning is the shallow depth of many quakes, between 10 and 15 kilometers, indicating heightened crustal stress. Though scientists remain cautious, the timing of these seismic events coinciding with intense solar flares has drawn attention to the possibility of solar-terrestrial feedback mechanisms. There is historical context that adds weight to this observation. In early March 2011, during increased solar storm activity and geomagnetic disturbances, a magnitude 7.3 earthquake struck the same region, followed 2 days later by the devastating magnitude 9.1 event. While there is no direct proof linking solar storms to major earthquakes, ongoing research suggests that solar-driven disturbances may play a secondary role in earthquake timing. Solar storms can activate Earth's ionosphere, change atmospheric pressure patterns, and influence the flow of electrical currents along fault zones. This sequence of effects, ionosphere to atmosphere to lithosphere, may in some cases act as a trigger for already strained tectonic systems. The lunar cycle adds another layer of influence. During new moons and full moons, Earth experiences stronger vertical ground displacement due to tide amplifications, which can increase stress along shallow fault lines. The current seismic swarm in Japan aligns with a new moon phase and an approaching geomagnetic compression period, raising reasonable scientific interest. Dr. Kayla Ryan emphasizes that such events should not be seen as predictions but as signals. In his words, patterns do not predict, they warn. If its orbital path remains stable, 3IR Atlas is expected to reach its closest approach to Earth on the 19th of December, passing within a range that allows better observational accuracy, but still at a safe distance. What makes this period significant is not proximity alone, but the timing relative to ongoing solar activity. As long-lived sunspot regions rotate back into Earth-facing view, solar flares and CME emissions may intersect 3IR Atlas's vicinity. When solar wind streams pass through electrically active comet tails, they can alter the comet's ion tail structure, potentially causing visual and electromagnetic changes that may be detectable from Earth. Some space weather models suggest that a solar storm in mid to late December could brush past a comet's position, possibly triggering a visible transformation or irregular plasma tail expansion. Looking ahead, January 9 stands out as another noteworthy date. On that day, a rare planetary alignment will occur where Jupiter, Earth, the Sun, Mercury, Venus, and Mars form a near-perfect geometric line. Jupiter's powerful magnetic field, the strongest of all planets, will be positioned opposite Earth, while the inner planets align behind the Sun. This configuration could enhance the solar wind funneling effect, directing charged particles more efficiently toward Earth's magnetosphere. Although not extreme or catastrophic, such conditions may produce stronger auroras, unusual fluctuations in the magnetosphere, brief pole drift behaviors, and temporary satellite disruptions. This alignment does not cause physical events on its own. Rather, it may amplify ongoing energetic phenomena already active within the solar system. The combined effect of magnetic symmetry, comet proximity, and solar activity creates an energetic environment worth monitoring, not fearing. As Dr. Kayla Ryan explains, planetary alignments don't cause events, they synchronize them. Recent coronal mass ejections have not only triggered geomagnetic storms but have caused structural changes within Earth's radiation belts. Under typical conditions, our planet hosts two stable Van Allen radiation belts. However, after the recent G4 and G5 geomagnetic disturbances, satellites from NOAA and the European Space Agency have confirmed the temporary formation of third and even fourth energetic particle layers. These additional belts are created when high-energy particles become trapped in Earth's magnetic field, forming plasma storage loops that can last for weeks or even months. Similar phenomena were last recorded during the Halloween storms of 2003 and during intense solar activity at the peak of solar cycle 22. Scientists describe this phenomenon as solar energetic memory, where Earth's magnetosphere remembers major solar events by holding and recirculating trapped energy. These belts gradually decay but can influence space weather significantly over time. They increase the probability of auroras, affect polar satellite communication, and cause disruptions in GPS accuracy due to ionospheric distortion. Aviation routes over high latitudes may require monitoring due to radiation spikes, and satellites may experience increased drag and surface charging from energetic particle bombardment. Entertaining this elevated energy state, Earth is likely to remain in a high geomagnetic cycle for the next 2 to 3 months, making it a valuable observation period for researchers and space weather scientists. As solar activity continues and more CMEs interact with Earth's magnetosphere, the temporary radiation belts could shift, merge, or collapse in irregular patterns. Instruments aboard NOAA's Discover and ISA's Swarm satellites have begun detecting the early stages of these plasma reorganizations, confirming the persistence of stored energetic particles well beyond the initial flare or storm event. The long-term impact is not immediate or dangerous, but it marks a scientifically rare opportunity to study Earth's magnetic endurance in high-energy solar phases. Science is guided by observation, but it must remain careful not to turn coincidence into causation. Comets do not control solar flares, and planetary alignments do not directly trigger earthquakes or storms. Yet, they may contribute to environmental conditions where certain events are more likely to occur. They may help shape timing, not force outcomes. What we observe is not control, but synchrony, subtle interactions among magnetic fields, charged particles, solar wind flow, and orbital timing. Nature does not operate through isolated events, but through networks of influence, cycles, and harmonics that we are only beginning to understand. Patterns help us see, but they can also mislead if we assume too much. Science progresses not by claiming certainty, but by refining how we ask questions. It is possible that future studies may reveal deeper energetic relationships between celestial motion and solar behavior, but for now, we recognize only that timing, symmetry, and resonance sometimes overlap in intriguing and meaningful ways. They may not create events, but they may align the conditions in which those events unfold. As Dr. Kayla Ryan says, the more we measure, the more mystery we find. There is order, but it reveals itself slowly. These recent events remind us not to fear the skies, but to observe them. Earth is not an isolated world. It is part of a constantly moving, responsive, and interconnected solar system. Solar flares, planetary alignments, comet trajectories, and magnetic storms are not just scientific data points. They are expressions of a larger rhythm in space. For researchers, astronomers, students, and even casual sky watchers, this is a meaningful moment to pay attention. Understanding space weather help protect satellites, power grids, and communication networks, but it also deepens our relationship with the natural order of the universe. In the coming weeks, new solar imaging, magnetosphere data, and trajectory updates for 3IR Atlas will be released. Observatories and space weather agencies will issue aurora alerts for higher and mid-latitude regions. These are not signs of danger, but chances to witness the beauty and activity of our star and its influence across space. Watching the sky with awareness brings knowledge, humility, and sometimes even wonder. As Dr. Kayla Ryan often says, the sun is speaking, not loudly, but rhythmically. And when we learn to listen, we begin to understand not only the stars, but ourselves.